السلام عليكم.
وعليكم السلام ورحمة الله.
ننتظر إن شاء الله. يعني دقيقتين تلاتة كده الناس تدخل، بعدين نبدأ إن شاء الله. إيه الأخبار يا جماعة؟
الحمد لله تمام. ازيك انت يا دكتور؟
حضرتك.
الحمد لله الحمد لله. إن شاء الله النهاردة هتبقى سيشن خفيفة خالص. um, we will talk about the model evaluation. وبعدين إن شاء الله نتكلم شوية عن ال capstone project. اللي حابب يعني يشارك في البروجكت ونشوف يعني نتكلم عن البروجكت بشكل عام ونشوف يعني الناس حابة تعمل ايه. آم، sorry I got distracted. فخلينا نبدأ كده إن شاء الله. آه، طيب
ممكن سؤال قبل ما نبدأ دكتور؟
اتفضل طبعا.
انا ما اعرفش، يمكن عندي مشكلة بالديسكورد but I did not receive a recording of the last session. اي نمبر 1. والنوتس اللي حضرتك حاططها على البروجكت هاي بتخص الناس المشتركين بس بالكابستون بروجكت اللي initially عملوا ريجستريشن، مش كل الاودينس، صحيح؟
هو يعني آه الانتنشن كان انه هيبقى في more people to do the project than we can handle in terms of عدد الناس يعني عدد الناس الموجودة كان هيبقى في projects كتير. أم، فكرة إنه يعني to mark the projects أو إنه to review all the projects كان هياخد وقت كتير.
مهم.
بس given إنه a lot of people just يعني dropped out أو stopped attending. I think I would like to give more priority للناس اللي لسه موجودة لحد آخر الكورس.
مهم.
ان هم يعملوا البروجكت. فيعني في ناس عملت registration من اول ما الكورس بدأ وكده، ولكن they haven't been showing up for the last few classes. فما اظنش انه حد اصلا هيبقى مهتم انه يعمله. ف يعني فكرة ال registration في الأول was just to limit the number of projects that we can handle reviewing، عشان الموضوع العدد لما بأول ما بدأنا كان كبير قوي.
مهم.
ولكن everyone who is still here is welcome to do the project, and I'm happy to review their project work.
اوكي، that is good news.
بالنسبة للريكوردينج دكتورة مريم إن شاء الله يعني إن شاء الله will upload the recording from last time. I imagine she must be busy given the academic year has started. بس إن شاء الله يعني give her some time وإن شاء الله she will upload the recording
That's okay, no
بإذن
problem.
الله.
I thought I only had a problem لأنه الديسكورد عندي مش عم بيعمل update، ففكرت إنه I'm the only one who didn't get
مم.
it.
لا لا if you have seen the post اللي أنا عملته امبارح أو النهاردة
Yes,
عندكم،
yes.
يبقى هو يعني خلاص you're getting the messages.
Okay, great. Thank you. I'm looking forward للبروجكت إن شاء الله.
إن شاء الله. طيب any other questions before we get started إن شاء الله؟ طيب تمام. أم طيب احنا إن شاء الله يعني هناخد بس some we will talk about some formal discussion of how to evaluate the models. So احنا so far يعني everything we've been doing in terms of evaluating how the models work when we change some meta parameters or add some regularizations or anything in that regard. We were just looking at one thing, um, or actually maybe two things. Like we were looking at the how the loss changes throughout the training, and then this is obviously something you wanna, as you are training a model, especially models that take longer to train, you would like to see that the loss decreases over time, which points to which points to the model learning from the data as the training goes on. And then the other thing was the accuracy, and the accuracy was simply we were trying to see compared to the ground truth that we have, how many, if it was a classification task, for example, how many examples do the model get right compared to the ground truth versus how many like mistakes does the model make. So there is a little bit more nuances when it comes to model evaluation, and that's what we're hoping to cover today. So this is something that you might have seen before in other courses or in other fields. Typically, when we have any classification problem, um, I don't know why my pointer is getting super slow. Okay, it's fine now. No, it looks like it's laggy. Anyways, um, for any, um, hold on, I know what to do. Hmm, Okay. Um, Yeah, sorry. I was saying for any classification problem, usually if you're trying to understand the performance of the model, there's something called confusion matrix that we look at, and confusion matrix is called confusion matrix not because it's confusing, but because it tells you how um, how confused the model is. I think this is how I understand it. Maybe this is not true, but this is my intuition for it. And it's basically like a very simple table that takes the classifications that the model do and compare them to like the ground truth or like the true labels that we have. And one example here, very popular example in machine learning courses in general that you see like if you would like to train a model that detects spam emails. So you have a case where you get an email and then you have some algorithm in place that tries to either classify this email as being a spam email, so it sends it to like your junk folder or your spam folder, or this is not a spam email, so it goes to your straight inbox. And this is quite important for certain applications because, I mean, personally, to your personal email, you would like to not have any like malware that comes to your inbox, or you click the link and then someone hacks into your computer. But this becomes even more important if you think about like government institutes or things that have sensitive data. If someone sends just an email to any of those domains and someone, there's first of all a filter that is not good enough and the email just makes it to the regular inbox. And then someone clicks on it and then all of a sudden you got like some data leak from this government institute or whatever. So this, in some cases, could be very important. To give you an example, for example, at my company, they usually have these trainings for us, how to detect spam emails, how to report spam emails, and sometimes they would send like fake spam emails with fake links to test who actually clicks on these spam emails versus who reports the emails properly. And these could be things like, around holiday times, they would send like gift cards or something, and some people fall for it. They just get excited and forget to check that this might be a spam email or something. It's funny, but it's actually very useful to a company to protect their assets. So, like typically, in a like in an output, as we said, we can have one of four possibilities. Like on this axis here, you have like the ground truth or like the reality of the matter, that it might actually be true that this is a spam email, or it might be false that this is a regular email. This is not a spam email. And then on the y-axis here, you have the model prediction. And the model prediction could either be, again, true that this is a spam email, or it could be false that no, this is a regular email. So we end up with one of four situations. It's either that you actually get a spam email and the model correctly classifies this as being spam. So this is what we call a true positive. So it is a positive that this is an actual spam, and the model correctly classifies this as a positive or as a spam, which is the true positive. You can get a case where you have a regular email going to your email address, but the model is falsely calling this as being spam. You kind of see this maybe many times where people are like, "Oh, if you don't get this email, maybe check your spam folder, check your junk folder. Maybe it just incorrectly went there." Especially it's from an address that is um, not yet, not something that you've received an email for, or using a domain where it's kind of popular that has like some word in it like info at something or so, which the a lot of the classifiers tend to classify as like junk emails. But you will hear this often from people if you're expecting to receive an email and they're like, oh, if you don't receive your email within 2 days, maybe check your spam, that maybe it went there. So this would be the case of this actually is not a spam email. So this is a good email you would like to have in your inbox, but the model falsely classifies this as being a spam email. And this is called the false positive. On the flip side, you have the model, you have a true spam email, so an email that you don't want landing in your inbox, but the model actually mistakes it and says, no, this is not a spam. So the model's prediction is that this is a safe email. It should not be labeled as spam. And this is obviously a false negative because the model classified this as being negative, so as being safe, but this is wrong because in reality, this is a truly spam email. And then you have the fourth case, which is like this is a regular email, and the model classifies this as being um, also safe email, not spam. So this is like a true negative email. So this is, you probably might have seen this before, some form of it. There's also other names for this, like you might come across the false positive being called a type 1 error and the false negative being called a type 2 error. The concept is the same, and sometimes, as we probably said this many times, in different fields, the exact same thing mathematically can be called different things depending on the domain of knowledge itself. But they really mean the same thing. So this is what we've been really doing in terms of like in our evaluations and in the plots that we were doing after we trained the models. We were computing the accuracy, and this really is I like to think about like with every metric that we're going to cover. I like to think about what question does that metric really help you answer. And in the case of the accuracy, it really helps you answer this question, which is out of all the predictions that the model has made, what fraction did the model get right? So we're taking the number of the correct predictions that the model made, and these correct predictions, if we go back to this picture, are the true positives and the true negatives, because this is where the prediction of the model matches the ground truth. So these are the predictions that the model has made in both the positive and the negative situations. And this gets divided by the total number of predictions that the model made. So if the model will make some predictions in all of these boxes. Like maybe some of them actually might be zero. Like maybe the model doesn't have any false positives or any false negatives. And that's actually what you want to see. But like your denominator for this equation is the total number of predictions. So in other words, again, we're looking at all the predictions that the model have made, which is the denominator, and we're trying to see how many of them did the model get right. So, I mean, this is pretty intuitive, but then can you think about some examples or situations where the accuracy actually falls short? Like if I'm just taking the model's predictions and comparing them to the total number of predictions that the model made, um, why is this not a good enough metric so that we actually need to go and, come up with other metrics to evaluate the model? Can you think of any examples?
unbalanced data يعني لو
Yes.
في مثلا.
Yes. So can you elaborate, يعني Sandra, what happens if we have unbalanced data? Why would we want a different metric, and what would that metric look like?
أم، يعني لو عدد مثلا في dog و cat
Mm-hmm.
الكلاسيفيكيشن، لو عدد الداتا مثلا عندنا 100 photos of dogs
Mm-hmm.
و
Mm-hmm.
ومثلا 20 of cats.
Mm-hmm.
الكوريكت يعني هو هيبقى biased already للdogs.
صحيح. صحيح.
عطوط.
And
بس مش
yeah,
عارفة ايه الحق يعني، ايه
yeah.
البديل يعني للأكيورسي.
Okay, so this is very good intuition. This is exactly the problem. And I mean, um, if you have unbalanced data, and you mentioned an example that is actually quite easy. So if we have 80/20 is not as extreme, but if you're trying to build the model to detect a rare disease, okay, or in the spam emails, by the way, there's way more regular emails than spam emails, for example. So this is already an example of unbalanced data. Or another example is if you're working for some company that tries to detect like fraud credit card transactions, for example. So there's way more regular transactions than fraudulent transactions, for example. So the percentage of the two things that you're trying to classify by nature is very different. So the example we have here is like if you're trying to detect a model that detects a rare disease. So by default, this rare disease maybe is in 1% of the population. Maybe it's even less, 0.5% of the population. And that's actually pretty common situation that a lot of the diseases are not like, present in 80% of the people or whatever. It's usually a smaller percentage of the population. If you are to train a model, any model that didn't learn anything about the data, like the model that absolutely learned nothing, will have like for every 100 patients, if the model always predicts that you don't have the disease, then the model is going to be like out of these 100 examples, it's going to get 99 examples correct, right? So like if the model doesn't really do anything, the model just predicts that it's a no disease. So every example you throw at the model, you run it through the model, it tells you, no, this is a normal, this is not a disease case. Because of the distribution of the actual prevalence of the disease, that it only occurs in 1% of the population, the model is going to be 99% accurate, which sounds really good, but it really is nothing because the model really doesn't do anything useful. Does that make sense? So in your case, yeah, Sandra, like if we have 100 pictures of cats and 10 pictures of dogs, and the model just predicts cats every time it just says this is the picture of a cat, then the model is going to be 90% accurate without even trying to learn what a cat is or what a dog is. And that's why the accuracy in that case is going to be misleading. I would think like, oh, I have a model that is 99% accurate, but the model really hasn't learned anything and it's not useful in that regard. Okay, so what can we do? Um, let's come up with other metrics. The metrics are not really um, drastically different. We will just think about the math in a slightly different way. So one of those metrics is called the precision, and the precision only focuses about uh, the true predictions of the model. Sorry, the positive predictions of the model. So we're looking at this the top row here. So we're ignoring the negatives for this metric, and we're just looking at the positive predictions that the model makes. So we're trying to answer the question of all the times the model predicted something to be positive or true, how many times was the model actually correct? So we're looking at the number of the correct positive predictions, which is this still the green box here, and we're comparing this only to the true positives plus the false positive situations. So we're not really concerned here about the negative predictions of the model. We're only concerned about the positive predictions of the model. And again, this is a metric that helps you um, kind of trained towards having very few false positives. Like for example, in the case of the email that we just described, if you have good precision or the precision can help you answer the question of is the model trustworthy when it predicts something as being positive? Because if the model is actually hiding some emails from me because it's classifying these as being spam while they're not in the spam, you're practically missing some emails that you should be getting. And again, you could also argue the other way around, and we're going to talk about this that, oh, but if the model is actually doing this really well, but it's also giving me false negatives, meaning that some emails should not be coming to my inbox and they're still coming to my inbox, this is also bad. So no arguments there. This is also true, and we're going to talk about the balance of these just in a few minutes. But yeah, but here, so the precision, you would prioritize your precision scores when you're training the model if you really care to minimize the few false positive, if you really care to minimize the number of the false positive uh, predictions that you get from the model. Okay. And then the other example or the other metric that we can use is called the recall. And in other words, also called the sensitivity of the model. And this actually looks at the all the true values. So it looks at, again, this, instead of looking at the top row here, it looks at this column here, which is basically we're looking at all the true cases. So we're trying to answer the question of the actual positive cases, which is like the ground truth positive cases. So again, in our example of emails, in all the truly spam emails, how many of them did the model successfully identify as being spam emails? Okay, so here we're not really concerned about the the um the cases where the reality itself, the ground truth itself is negative. We're concerned about the cases where all the emails now that I know for sure are spam, how many of those did the model classify them as truly being spam? So we're comparing the true positive of the model to the sum of all the cases that are true, which are the true positive and the false negative. And again, this is a metric that we prioritize. We try to push to be as high as possible if we really care about minimizing the false negatives. And one example to think here is in a medical diagnosis, for example. I would rather have a test classify patients as being false positives, like For example, you go and you're doing, I don't know, COVID test, for example. So you do a preliminary test, and the test is really making sure that it doesn't miss any case. Because if a patient comes to you and you send them home saying, "Oh, you're fine," and this patient is in reality infected, he's gonna go home and infect other people thinking they're fine, for example. But if you tell someone, "Oh, it looks like the test that you might be positive," then it's going to be maybe there's a follow-up test that the patient can take to either confirm that they have the disease or to um, say, "Oh, no, no, the first test was a false positive." The second situation is a much, much more favorable situation in a clinical setting. You would rather tell someone that you might have something, so it warrants further testing, then you tell them, "Oh, you're fine," and yet you're actually missing the detection of a disease early on, or the person is infectious, so like you're sending them to mingle with people and spread the infection without knowing that they have a disease. So this is a case where you would like really to minimize any false negatives. And in that case, you would really look at like your recall and make sure that this value is highest as possible. Okay. And then this is, what exactly I was mentioning is that you will find naturally that as you're trying to um, basically optimize for precision or recall, that you're going to have to do a trade-off. Because if you try to increase the recall, if you try to make the model really, really good at not predicting any false negatives, by default, the model is going to predict a little bit more false positives, and vice versa. If you try to make sure that the model doesn't really, really classify any false positives, like you really want to have anything classified as a false positive, you will find that by default, you're going to increase the chances of the model making a classification as a false negative. So there's always this balance or the trade-off between precision and recall. And depending on the application that of your model, you always try and see what exactly do I really care more about? Do I really care more about not having any any false negatives, or do I care more about not having any false positives? And depending on this, you will pick which one for them is more important to you, and then you would tune your training towards that evaluation metric. Any questions? Hopefully, this is quite easy to ingest. Okay. All right. So the last thing, and this is actually the pretty popular one that a lot of people use, is called the F1 score. I don't really know what the or where the um, F1 score come from. If you know, please let me know. I never looked it up actually, but anyways, so the F1 score, this is basically kind of a way for people to have like a balanced measure. It's something that you can think of similar to the accuracy because it gives you kind of an overall score to the performance of the model, taking into account both precision and recall. So the F1 score can only be high if both the precision and the recall are high. Not one of them. Both of them both of them have to be high for this F1 score to be high. So if you take, for example, a situation where you have um, good accuracy, like 80% accuracy, but then you have precision that is like 85% and recall that is like 60% or something. When you do the F1 score, you will find the F1 score mathematically is going to be less than the accuracy. And then this tells you that when you see a difference between F1 score compared to the actual accuracy, this tells you that one of the two things, precision and recall, is not really high enough. So you know you have a problem. Okay? The math behind the F1 score is something called the harmonic mean of precision and recall, and this is how it's computed. Um, I don't really have good intuition for this equation right here. That's why I put the other one, which is, I think about it this way. You're taking the number of true positives, you're taking the number of true positives, and you're dividing this by basically like we take these three uh, uh, boxes here or three categories here as our denominator, except that we're taking the average of the false positive and the false negative because we're trying to balance the recall and we're trying to balance the recall and the precision. So we take the average of the two sources of error, basically, and then we add this to the true positive as like the denominator. Does that make sense? Because like if you look at the actual precision or the recall equation, we take the true positives, which is the correct predictions by the model, and we divide this either by the total positive predictions or the total true cases in recall and sensitivity. Sorry, in precision and recall. And what we do here is we're basically just, for these two false terms, essentially, we're taking their average and then we're just computing the F1 score. This, for me, the math here is a lot more intuitive than this. Um, if you break this, like if you break this equation, like you actually break the precision into true positive over true positive plus false positive and do the math, they will basically be the same thing. Um, but anyways, if you are like studying F1 score or so, um, you will see the mathematical expression of the F1 term in either one of these two equations. The code implementation for doing these metrics is pretty simple. I gave you two examples. One is the very old and easy to do NumPy, which is a little bit more manual, but nonetheless, it's very easy because as you see, the math here is pretty simple, nothing really complicated to do. So assuming that you have ones and zeros as your output, um, this represents your true ground truth. So like the y true is the cases where not the cases. This is the actual ground truth of the model, and the y prediction is the prediction of the model. So one meaning here spam and zero meaning not spam, and you're trying to see um, how much the prediction of your model varies from the ground truth. So this is exactly the calculations for having the true positive, true negative, false positive, and false negative. You're just summing the cases where the ground truth is actually one and the prediction is also one. And the true negatives are when the actual ground truth is zero and also your prediction is zero. The false positive is the case where the ground truth is zero, but the model is seeing this as being one. And the false negative is obviously the reverse. And to do this calculations, essentially the accuracy, precision, recall, and F1 is just simply to use the same equations that we had here in the values that you created. So these are the values in your confusion matrix, and you're just applying the math here. There's a much easier way to do this from the scikit-learn library. So this is the second time we've seen this library. The first time was the very popular test train split function, which was splitting your data set into train and test, if you remember. And this is another very popular module from the scikit library called the scikit-learn metrics, where you can basically just, instead of doing all that, it's actually pretty simple, but instead of doing this yourself manually, all you need to do is that you call the function, so just call the function accuracy score, and you give it the vectors for the true labels and the predicted labels from the model, and it automatically gives you the accuracy score. Precision is the same, recall is the same, F1 is the same. So I just change the function name, you give it the true labels and the prediction labels, and it just computes whatever score that you tell it to. Another good thing here is that this is also the case for the multi-case classification. So everything we talked about here is pretty simple. It assumes a binary classification. So like you can only have two outcomes. It's either a spam email or a non-spam email. You can have a positive diagnosis or a negative diagnosis. So these are examples of binary classifications. But if you have pictures that you're trying to classify into 10 different animals, for example, you can have different performance from the model to each one of those animals. So maybe the model can recognize cats very well, but it cannot recognize horses. So it tells you like, oh, the model has learned to classify cats, but it hasn't learned to classify horses. Maybe I should increase the number of pictures of horses in the training data, for example. So the when you try and do this per class, when you have a multi-class classification, this becomes a little bit messier. You need to think about it a little bit more carefully, and it becomes a little bit more involved. When you use scikit-learn, um, it doesn't really change the function much, and it actually gives you a score for every one of the classes, but it can also give you the average score. Like if you would like to just look at the average precision of the model across all the classes, you can also do this using the same function. And all it takes is a few arguments. You can always check the documentation of these functions as you run them. And then it will tell you what to change if you would like to have an average or you'd like to export the individual scores per class that you're trying to classify. Any questions? Okay. That's actually all about it for metrics. When it comes to or model evaluation, when it comes to classification problems, the hold on. The regression problems actually are much easier because in regression you don't really have any classes or you don't have any discrete variables that you're trying to compare against. But the what is it called? In regression examples, you have a true value, and then you measure the variance away from that true value, which we typically do using the what is it called? The residual squares. So you look at the distance between or the difference between the ground truth and your predicted label, and you either do the difference in this if you're doing this numerically, or you do this as a distance if you're doing this geometrically on the graph. And then you sum all these distances, and this is actually what we use for the loss function. But if you're trying to quantify these, they are called the residuals of the model. If you're trying to quantify how much your values are away from the ground truth, these are called the residuals of the model. And again, there is no notion here of being a positive and a negative and true and false because this is a continuous scale. And what you're trying to do in terms of metrics is you're trying to minimize the distance from the ground truth to your predicted values. So it becomes a more straightforward approach. There are some you know, like board concepts from statistics, for example, like the R squares. You know, when you do like the linear regression and you do the R squared to look at like the regression and how one variable can predict the goodness of the other variable and stuff like this. These are not really very specific to deep learning, but these are kind of board concepts from good old statistics of like linear regression and stuff like that. Pretty sure everyone here has gone through doing like manual linear regression example on those graph sheets, the orange or pink ones, and manually computed the R square values and stuff like this. So hopefully this is stuff you already know. And if you don't, there is like very easy ways to do this in Python. There's the SciPy stats function. There's also a lot of R libraries if you code in R, and these are hopefully pretty straightforward. Um, any questions about like model evaluation? Let me see. Oh, the chat. Um, why the harmonic mean in F1? Like, is your question why do we use the harmonic mean, Omar? Um, the harmonic mean is I think I don't know much about the harmonic mean, but my what I know or what I read is that it usually is used when you're trying to average ratios or you're trying to average rates. So like if you have something like velocity, for example, which is a rate of change over time, or if you have ratios, like in our case, we have the the recall and the precisions are essentially like each one of them is a ratio in and of itself, and you're trying to average these ratios. mathematically, this is what the harmonic mean is for, is when you have rates or ratios that you're trying to average. Why not use arithmetic mean? I don't really know. I never really looked it up, but I'm sure there's some mathematical reason of why exactly why harmonic means are preferred to be used in ratios and rates. Um, if you're curious, maybe you'll look it up and let us know. I would be also interested to learn why, but um, I didn't think about it before. Good question. How do we fix the model once we have these scores? Oh, you tell me, Sandra. How do we fix the model after we have these scores? You tell me.
I'm not sure, but it depends,
So
I
so
think, on the
so so
score.
so if the model is not doing something, if the model is not doing something that you expect, how do you how do you make the model, or how do you try to make the model perform better?
Tuning the model,
Yeah,
trying to change the
exactly.
hyper, but like
Yes, exactly. So you
experiment
try to
with that.
tune the model.
Okay.
Yes, exactly. So you think about your architecture, you think about your training data, you think about the parameters that you're using, the meta parameters that you're using to train the model, the learning rate, the balance of the examples, the training, the testing. Do you have good testing data? Is it orthogonal to the training data? Are you using good learning rate? Are you using a good optimizer? What does your batch size look like? Is it maybe the batch size is too big? Maybe it's too small. Are you using good regularization? Are you normalizing your data? Are you doing batch normalization? So, and these are, this is a good segue then to talk about the capstone project. But I mean, before we get there, does
Yes.
anyone have any questions, either to the model evaluation or otherwise? No questions. Okay. I'm gonna share the basic this is basically the Discord. So um this is the post. Hopefully you've seen this. Um so the goal here in this project is for you to build a classifier in neural network. Um I suggested this last time. I suggested this many times that you go on Kaggle and find some data sets. I think it was you, Sandra, who suggested that I give you some examples. And I said, you know what, you should go and find your training data sets. But I caved and I gave you some examples for data sets. Actually, I asked Gemini to suggest these. Well, not these specifically. I asked Gemini to suggest something that would be reasonable for this project. And these are three suggestions that Gemini told me. I looked at the data descriptions and they were, pretty okay. So you can look at the descriptions of each one of these data sets. You can look at how many features it has, how many data points it has. Um, they're different, but they're also very similar. Some is related to, one is like on diabetes, the other is heart disease, and the third is like breast cancer. So look at them, pick your favorite. If you don't like any of them, you can, browse on Kaggle and pick a very different data set you know, that you like more. These are also binary classification examples. So I think the outcome for them would be, for example, for diabetes is like, is this a diabetic patient or not diabetic patient? For heart disease, it's the same. For breast cancer, I can't remember for breast cancer what it was, but I think the three of them were binary classifications, if I recall. But you can also look for examples where you have what is it called? Multi-class classifications. So you don't really have to do a binary classification example. It's obviously simpler, but it's an open invitation. You can do whatever you would like to do. So some things to think about to just try and be systematic on how to approach this. The first thing that you want to do in any project that is deep learning related or machine learning for that matter, um, is you want to look at the data, right? So you would like to see like what are the features that I have? What are the types of the features that we have? What are the distributions of the features that we have? Um, do I need to clean up the data? Are there any missing values? Is the data very, I don't know, sparse? Like there's like, 100 features, but there's only 10 examples per feature that have the data. So like maybe this is not a good data set to work with. Um, yeah, thanks, Omar. Yeah, malignant or benign. So again, it's a binary classification, malignant or benign. Um, then do you need to do any normalization or standardization to the data? Most likely, yes. And then obviously, after you've done, cleaning up your data, you understand your features and everything, before you do anything, before you touch the data, you have to classify your data into training, evaluation, and test. And you don't touch the test data sets until you get to the very end. You've trained your model, you've done your hyperparameter tuning, you've done everything. Um, Only then you get to the test data. But you don't try anything on the data before you split it. Okay? Again, we also did an example with training and testing only. And then it was one of the assignments I told you, like, how would you do a training, evaluation, and testing? Because the, train test split function from the scikit-learn doesn't really give you a train and doesn't give you an evaluation and test data sets. It only gives a test and train. So that's something for you to figure out. And it's very easy if you think about it. Um, and uh, um, yeah, so usually a silly example I'd like to say here. Um, think about um, think about having one knife and a piece of fruit that you would like to split into three parts. So what do? The knife doesn't cut something into three parts. It usually just cuts something into two parts. So what do? You cut twice, right? Okay. So model architecture, we obviously only did feed-forward neural networks. So this is what I expect you to use. But if you would like to explore something else and you would like to do an autoencoder, for example, or something like this, by all means, surprise me. Something to think about though is like how deep and wide would you like your network to be? This is not something that we spent a lot of time doing um, because there's really no strong consensus on how to do this. It's usually a choice that you make depending on the complexity of the model that you're training, the amount of training data. We kind of did this in a way to show like overfitting or underfitting depending on what you're trying to do and the number of parameters in the model. But maybe this is now a chance for you to explore, giving the data set that you're going to pick, what is a sensible depth of the network and what is a sensible width of the network. By the way, yeah, it even says here, the depth is the number of hidden layers that you use, and the width is how many nodes per layer. Um, Obviously, your input and output no layers are kind of pre-selected for you because the input layers are going to be the same number of features in your training data. So like we use the iris data sets many times. Every time we had an input of 4 nodes because we had 4 features in the data set. If your data set had 20 features, then your input's always going to be 20. And the output is now you have a binary classification. So you're going to input just a single node that has one or two. Or if you want, you can do 2 nodes and one with a probability of one, like class A, and one probability of class B, but it's not very popular. Think about the activation functions you would like to use. I think we talked about what activation function is usually used when you have a binary classification. So go back and double check this. Think about the activation functions that we'd like to use for your hidden layers. And then, so that's for the actual architecture. And then for your hyperparameters. So we talked about a few things. Last time we talked about the optimizers. And I told you usually a good place to start from Atom. But if your data is homogeneous enough, that's something you're going to learn from looking at the features. You can get away with using the SDM, the stochastic gradient descent. SGD. I don't know what SDM is. Stochastic gradient descent, SGD. Um, I was thinking about RMS. Sorry, this is how it came through. Anyways, learning rate. You can think about how fast or slow you would like your learning rate to be. And you can look at one thing here. You can look at your loss over time as you progress in training. Like if you know loss changes after 100 epochs by a tiny, tiny bit. Maybe you're training too slow, so you're going to take forever to converge. If your training, if your loss is actually increasing, then you're jumping over minima and you're overshooting. So maybe you need to slow down a little bit. Batch sizes, again, usually a good place to start, depending on the data set, is somewhere around, I would say, 64, 32, something in that space. Sometimes you want to go less, sometimes you want to do more, again, depending on the how homogeneous or heterogeneous your examples are. The more homogeneous they are, the better the model does with smaller batch sizes, and vice versa. Regularization. You can experiment with dropouts. You can experiment with adding L1 or L2 regularization. Again, we talked about what every one of those does and why you would want to pick one of them. Or you can do an elastic net regression and have a balance of L1 and L2 if you think that this is something the model would benefit from. And obviously, you want to train for sufficient time. Like you don't want to cap your model at like 100 epochs and think that your model is not learning anything when in fact you're just not training long enough for the model to you're not training long enough for the model to learn. So these are some of the things. Hopefully we discussed every aspect of these hyperparameters here in details in depth. And you have a good understanding of them and you can apply them and think about how to vary them and perform some parametric experiments to try and pick the correct hyperparameter for your model. And then eventually just apply the stuff that we've discussed today, the model evaluation. So again, think about in the metrics that we've done, obviously like calculate all the metrics, but think about all the metrics that we've talked about today. Think about the model that you're training and the application of that model. If you are to use that model in a real world situation, like for example, the diabetes case, do you want to give the upper hand to precision or recall, or do you not care? So think about the application to your specific use case. It's nice to visualize the training process, as we said, so that these are all very manageable data sets. It's not going to take ages to train, but it's always good practice to have a way to look at the models as they are training and monitor the training process itself. In case you need to intervene early, stop the training, make some changes, and restart again. You don't want to train the model for a couple of weeks and then find out that, oh, maybe there was something silly at the beginning that I should have changed. And had I looked at this a day into the training, I would have realized and I would have restarted. So you saved yourself a couple of weeks just by monitoring what happens as the model is training. What else? Yes, and then eventually, you would like to actually make sense of this. Like, this can very easy become very abstract and very, much like a number games. But eventually, hopefully, by the nature of these data sets, you get a feel of this is actually real data. This is actually something that can be used to help patients or have some real world application. So you would like to kind of evaluate your model in that sense. In the context of your project itself, did this model do a good or a bad job? And we mentioned this a couple of times, that maybe you arrive at the conclusion that I tried to optimize the model with so many, parameters and everything, but I could never get the accuracy of the model, the precision of the model above 80%. So maybe this is not the tool to use. Maybe a different architecture is needed. Maybe I should actually not use deep learning at all. Maybe the data is just better for another kind of machine learning method that I should use. These are all like okay conclusions to have. Like you don't really like the goal here is not try to train a model that is 95% accurate that I could just use in the clinic. That's really not the goal. The goal is for you to go through this process. Think about the different aspects of training that you want to do. Think about your data. Find the best way to get the best performance out of this model, and then reflect. Was this a good experiment? Was this a bad experiment? Maybe the answer is, oh, we need more data to train the model. And this actually, in a lot of cases, this is usually the case. Like for us, for example, we have lots of pitching to leadership to make of, we actually really need to generate data for in this kind of data for this kind of pathology because this is going to help us train better models, for example. So we can spend all the time we want to play around with the architectures and our parameters and everything. But in reality, if we don't get more data with more diversity, no model that we can build or tune is going to learn. So the answer is we need more data. So you can arrive at this conclusion, but you have to go through, you have to exhaust the options to arrive at this point. And again, this is a capstone project for an introductory course. I don't expect you to exhaust every option, but I expect you, hopefully, with what you've learned, to do enough so that you at least have an understanding of the process. It's a very iterative process. You do something, it's not working very well. You improve something, it works a little better. You improve another thing, it works a little better, and so on. Until you eventually kind of cap the performance at some point, and they're like, okay, this is the best I can do given the data that I have and the resources that I have. In terms of deliverables, and we can talk about this, see what people think. I think the basic thing to deliver here is going to be like a notebook. It could be a Jupyter notebook, it could be a Colab notebook, whatever works for you. It should be a little bit of an introduction. So like a problem statement, defining your data set that you picked, what was the problem in the data set, how many, examples you had in the training, whatever, how much data cleanup you had to do. And then obviously the code for cleaning the data, the code for building the model, and some baseline training, and then some of the hyperparameter experiments that you explored in terms of optimizing them. You don't really have to include everything that you've done in the final notebook, but like on the side, maybe you can run a few experiments and then you can save the results and put them as like some plots so that you can say, I looked or I went through optimizing these parameters. This is what I found when I don't know, did like the accuracy across different regularizations or did the accuracy across different learning rates or what have you. And this is kind of just nice to show like a summary of the hyperparameters that you try to tune in the model. And I mean, obviously, you have your final model evaluation on the actual test data that you haven't touched from the beginning. Remember, you're using your evaluation test or your def test set to check as you're changing the hyperparameters, but your test set is saved until the very end of the process where you're happy with everything and you're just going to apply this to the test data set. And this is where you use to calculate all the metrics, you still can calculate the metrics, obviously, for the train and the dev, because this is how you're going to know what the model is doing. But you also calculate this for the test data set because this is your final readout. Now that, that model now is ready to be published, you can then, as the new data comes into that clinic or whatever, then they just input the data into the model and hopefully they get a good prediction out of it. So there's two options here. You can either just post your notebooks and I can, look at them and make some comments, or you can ask me questions, or however you want to do it. Or we can have like maybe a session like this where you take turns and maybe spend like 10 minutes or something per person/group. And we just go through them together. This is really up to you how you want to do this. We can do some voting on this and see which way we want to go. Um, Also, you can choose to do this individually. Like you can work on your project individually and submit it. But ideally, I would like people to do this in groups so that we eventually have maybe about 4 to 5 maximum projects to review, um, so that I can give everyone a fair share of my time to, give them good feedback on what they have done, where they can improve, and um, if there's 20 of them, then it's a lot more burden on me. So maybe we can think about this and something to organize over Discord, that maybe we just limit it to 4 to 5 projects between all of the people who'd like to participate. And this is going to be a very reasonable number of projects to review and to go through together. And I feel like this is also useful for everyone to learn from their peers, like how they did. Maybe they did something that they hadn't thought about it. So I think it's a win-win to everyone. In terms of the timeline, I think, but I don't know what is reasonable. I think the reasonable is about 2 weeks, given that a lot of the training code and stuff is already in the notebook. So I mean, obviously you're gonna change it one way or the other, but it shouldn't be very hard, or not a lot of from scratch kind of code that you have to think about. And hopefully the concepts are straightforward, but I would like to give time for whoever would like to go back to the recordings, for example, and re-listen to the lectures to refresh their memory on some of the concepts as they work through the projects. I know that it's some people are in school right now, so um, you give me the timeline. Like my 2 week is like just a suggestion. If you need more time, if you think this is okay, let me know. But we need everyone to be on board so that we have a single session where we can review the projects together. Um, so I think I'm done talking now, and I'll leave it up to you to tell me what you would like to do.
Omar is saying if we maybe wait for 3 weeks for also for preparing the presentations as well.
Yeah. يعني عمر يعني presentation, you don't really have to do like a presentation style thing of like PowerPoint slides. And I think if you go through the notebook, but having like reasonable figures to show, like I think this could work. If you feel like you would like to do a PowerPoint presentation, this is also fine. But I'm trying to not have people stress over this as being, oh, I need to make like a very formal presentation. And, um, obviously, the better you present your findings, the better for you, for us, for everyone. But also, like, don't sweat it. Just keep it. Like the important thing is the time you spend on training the model and on testing and stuff like this. Um, and yeah, but I'm fine with 3 weeks. I'm not trying to negate 3 weeks. You're opening a can of worms, sort of. uh, yeah, we can have this discussion another time. I have to be sorry. I'm kidding, but this is a longer discussion. This is a longer discussion. Um, yeah, I mean we have time. Let's just get done with talking about the capstone project, and then I can tell you my story.
If I may, Dr. Omar,
Yeah, but
I think 2 weeks is a reasonable time, but as beginners, maybe we can just start for the coming week and get the feeling of it. Maybe we can ask for extension, maybe we think it's doable within the 2 weeks. A question is now, this is session number 10, and
Mm-hmm.
I'm not sure what is the plan for the upcoming weeks. So are we done now and we go to the project and we will reconvene when to discuss such things? So please elaborate.
Yeah. Yeah, so يعني hopefully inshallah this is the last session in the for the introductory course. يعني Allahu Alam what the future holds. But maybe we do an advanced course in the future. But for the time being, inshallah, this is the last session for this introductory course. Again, depending on what the people feel like doing, if everyone's just gonna post their notebook on the Discord and I give them some feedback, then that's that. If people would like to have one more session in 2 or 3 weeks, depending on where you decide you want to do this, for just people to present. This is going to be you presenting and me just listening. That's also fine by me. But in terms of additional sessions to cover more topics, I think this is it for now. Um, does that answer your question?
Yes, indeed. Thank you.
Yeah.
I will also vote for reconvening again and discussing the results rather than just sending them to you.
Okay.
And but I can also vote for an advanced course later on. But once we are done with the projects. But thank you very much for everything, Dr. Amr.
Yeah. You're welcome.
How would we make groups?
This is what the Discord is for. I'm not really, it actually took me a lot of time to even get the formatting of the text yesterday. I had to edit like 20 times. But I'm pretty sure there should be some polling, yeah, if anyone is a little bit more Discord, uh, yeah, sure. Omar is taking an initiative. He looks like he wants to work on the breast cancer data. If anyone wants to join, maybe just, yeah, make groups this way. Everyone here is a grown up. Everyone has done a group project one way or the other throughout their time at school, undergrad, whatever. So hopefully that's easy to organize. Um, so is everyone okay with the 3 week then? So like today is the 12th of October. 3 weeks meaning I have a conference in November, so I have to double check that I actually hold on. Um, so today is the 12th.
No,
3 weeks would
after
be
3 weeks, 2nd of November.
uh 1, 2, 2nd of November. Okay. Hold on. I don't know when my conference is. I mean it's a Sunday, so it should be okay either ways. Yeah. Okay, so 2nd of November. Let's write this down. Is everyone okay with this?
Fine by me.
Yes.
Okay. Okay, so this is set. 2nd of November. Can we write this in the session planning? Okay. All right. I put this in the session planning channel so that we don't forget. And then I think the um, hopefully we're gonna have, as I said, 4 to 5 people, so we can give about 15 minutes to every group. I think this is gonna be good timing if we have 4 to 5 and we have an hour and a half, so we have a little bit more of a buffer time. And obviously, as you work through the project, if you have any questions, please put them in the Discord channel. You don't want to be stuck in a rabbit hole, wasting a couple weeks on something that could be potentially addressed in a half hour. This is also an advice for life in general. Um, Usually, the problems you run into in deep learning or otherwise are problems that others have also run into before. So it's always nice to ask people for their experience in solving some issues that you're having, because sometimes, as I said, a half-hour conversation with someone could spare you 2 weeks of researching. So try to use me. I will try to be as responsive as I can. Maybe sometimes I will be a little slow in responding, but I will do my best to respond in a timely manner. Okay. Any other thoughts? Any other requests? I'm not going to intervene too much into what every group decides to do or how you organize yourselves or, you know, how basically you divide the work or how you do that stuff. In 2018, I think was my last year of TAing at McMaster, and we had some group projects. And I used to get emails 2 days before the deadline. So and so person hasn't done their job in the project, and we had a strict rule of you go down, the entire group goes down. I trust everyone here is an adult. I don't expect to see any um, complaints in that regard. So just saying, I'm not gonna intervene in any of the workload balance slash division slash what do you decide to pick. I'm just here to solve technical issues, and that's it. All right.
ممكن just a suggestion
Hmm.
لتقسيم الشغل. ممكن كل واحد يعمل، يعني حتى within one group كل واحد يعمل البروجكت أو الإكسرسايز كله، وبعدين نتفق مع بعض ونبريزنت حاجة واحدة، بس على أساس إنه كل الستبس احنا محتاجين نفهمها أو نطبقها كويس.
This is usually my attitude towards projects. Not necessarily that everyone has to do everything from start to end, but I always, when I had undergrad students, I always told them, don't divide the work in a way where one person depends on the other, A. B, where you don't really care about 80% of what happens inside the project and you're only focused on 20% because that's not the intention of having a group work. I agree with you in that sense. But like also to make it more efficient, you repeating the work of your teammate is not very efficient. So, for example, maybe you have a brief session of 30 minutes to look at the data. You just gonna look at what the data looks like, what kinds of features they are, what kind of things needs to be done, and maybe you just, decide that we do the cleanup, we arrive at the same data, and we split the data into train, dev, and test. And then you save the training data, the data, and the test data, because you don't want to have a different split because of how random things are. You don't want to have a different split that you're working on versus your teammate, and then everyone is getting slightly different results, and then you're trying to align them and you're having trouble. So I would suggest you do the cleanup together and then you save the actual training data, like you export this into like a data frame or whatever, and then you import it every time you're doing something so that you freeze it in that sense, if you will. And then you can start splitting the work at the stage of, okay, let's try and think about the model. So maybe I'm gonna train a little bit deeper model, you're gonna train a little bit wider model, and then we can kind of compare notes. So instead of
Yes.
you doing the thing, they doing their thing, someone is training something that they know, okay, I'm trying to kind of push the model to be a little bit deeper. So I'm gonna add more hidden layers. Someone is gonna know I'm gonna make the model wider, so I'm gonna add more nodes. And then you're comparing the outcome. So then you're learning. So instead of you going and testing this yourself, you tested one thing and then your teammate tested the other thing. Obviously, these two things, like code wise, you're gonna do the same thing, but you're just gonna be varying one thing or the other. So both of you have gone through the process of writing code to build the model, but one is doing a deeper model, one is doing a wider model. Same is for hyperparameters. Like for example, one is testing L2, one is testing L1 regularization. The implementation is slightly different, but you're kind of working together in tuning different hyperparameters at a time, and then you're putting things together at the end. So yeah, I agree to some extent with what Noor said, but also let's do it in a way that that is efficient and smart. You don't want to be redoing everything because then it doesn't become a teamwork. It becomes that everyone does their own individual thing, and then we're gonna pick the best out of them and just present this. Does that make sense? Okay. Um, any other comments? Type. We still have 15 minutes. If you would like, I can talk about my transition from wet lab to dry lab. Um, so actually, I had two transitions because the last time I've seen in the comments, Dr. Mariam put uh, a link to a session we had. Can imta? I think it was summer of last year, 2024. And at that time, I was actually a computational biologist. So I was not very much into deep learning, and I was a little bit like a little bit working on one project that was deep learning, but I also wasn't very much into the trenches of model training and stuff, if you will. So, um, my journey, I graduated pharmacy. I did my master's in it, the program was very course based, but then we had a few internships and a 6 minute sorry, a 6 months thesis project, which was on the microRNAs and stuff. So it was very molecular biology heavy, wet labby kind of project with lots of cloning, cell culture, stuff like this. Funny enough, when we were writing the paper for that project, we had some TCGA patient data, which I had absolutely no idea what to do with them. Even though the statistics were quite simple, I just asked my advisor to do the figures because I said, I have no idea how to do this. So I wasn't really into that kind of stuff. And then I moved to from Germany to Canada. I started my PhD. I actually worked for a little bit like as a research assistant for about a year and a half before starting my PhD. And in the beginning of my role before like as a research assistant, I think the PI gave me like a microarray data set that they were trying to analyze, and he was like, "Take this and see if you can get something out of it." And it was just a bunch of numbers in an Excel sheet, so it was like the processed microarray, wasn't like the raw data or anything. And then just Googled, how do I do this? And I found people talking about programming and R, and like, that's not for me. Sorry, that's not something I can do. And I told him, yeah, go find yourself a bioinformatician to do that work. I can't really do it. And then fast forward into 2018, 19, I can't remember. I decided to take an introductory course in bioinformatics. That was like in between, like the time when my advisor asked me to look into some microarray data. It was like 2015, and then by the time it was 2018, 2019, it was increasing number of papers that were using sequencing data, and single cells become a thing. And every good paper I read had some form of bioinformatic analysis in it. So I'm like, maybe I should learn what these people do. Maybe this is going to be useful. So I started taking like an introductory course to bioinformatics. It was one of their graduate school courses. So very formal course, good instructors in McMaster, good infrastructure, access to clusters and stuff like this. Every time in that course, we had like an assignment that we had to turn in. And the assignment was supposed to take about half hour to 45 minutes. And I think every assignment I spent about 4 to 5 hours on it, and I got like 3 out of 10 questions correct or something like this. And I just dropped out of the course. I told my advisor I don't know what's wrong. I mean, I emailed him saying that was the course instructor, not my advisor. I emailed him saying, how much time are you expecting us to spend on these assignments? Because I feel like I'm spending way too much time on them. And he was like, that should take you like about half hour, 45 minutes. I'm like, no way. It's taking me like 4 to 5 hours, and I'm getting most of the questions wrong. And I'm like, okay, that's not for me. This bioinformatics thing is not really for me. So I dropped out of the course. I didn't even finish the course. So then fast forward then to 2020 when COVID hit, everything was shut down. The lab was not able to get mice. So my PhD, sorry, I jumped over this, but my PhD was all like mouse work, like experimental work, mouse work, tissue culture, a little bit of primary human cells, even though none went into my thesis, but like a little bit of like just pure wet lab work. There is absolutely nothing, not even like qPCRs and stuff like this, just, tissue culture and mouse and experimental data and organ processing and flow cytometry. And it's just like nothing. Even flow cytometry data was like very manual analysis of like drawing the gates, manually writing the numbers in Excel to make some figures out of them and stuff like this, which like wasted hours of my time. I hated this, but anyways, um, yeah, 2020 was COVID hit, and what is it called? Oh, the lab shut down. Yeah, the COVID hit and the lab shut down, and we weren't able to get mice. I was the what year? Mid third year of my PhD or something, and I just was kind of freaking out that now I don't have mice to do experiments, to generate data, to finish my thesis, to graduate. So I thought about like one of my colleagues suggested doing a high throughput experiment where we just do some microarray or sequencing, get some data, and just with the analysis, just kind of expand it a little bit and essentially just spread the data into many sections and figures and try to just bulk up as much as possible. The problem is I had really no idea how to handle this data, and my PI has gone broke and can't really afford to hire a bioinformatician. So I found this microarray platform that has a little bit of a user-friendly software that comes with it. It was an assay called I think AFI matrix or something, and it was just long story short, if you buy some kits from them and you do some microarrays, they give you access to that software, which only works on Windows and has some restrictions. And that wasn't my plan. I convinced my PI to give me the money to do this experiment, and after the experiment was done and I used the software, the results were really bad. Like not the results in terms of the biology, but the analysis that I could do with that software was very, very limited. It was just put your groups here. We're going to give you a list of genes. They have very fixed downstream analyses that you can do. Like you're just going to do a Go enrichment analysis or blah, blah, blah. The only things you can change were like the threshold or how do you filter your genes, what p-value you use and what log fold change and stuff like that. So it wasn't very, not what I'd hoped for. So then I decided to bite the bullet and started learning, or how do people actually analyze this data to get to the, the bottom of it, to actually extract useful information out of it. And because it was lockdown time, I spent a lot of time at home. I tried to read books online, look for online courses, uh, and just lots of hours of frustration and feeling stupid and feeling like I can't do this. Eventually, things started working out. So then uh, one thing led to the other. I moved from microarray data to learning how to analyze RNA-seq data because I wanted to use some TCGA data to link what I'm doing in mice to what's actually happening in patients. I was working on melanoma mouse models, so I cared about some melanoma patient data. But to do this, I had to learn how to use the data from TCGA and how to analyze the RNA-seq data and how to link the metadata to the actual transcriptome, and then how to link this to what I'm seeing in like my mouse models and stuff like that. So again, it was a very long and tedious process of trying to teach myself. There was no ChatGPT at the time. There was no Gemini at the time. And it was just good old, Slack overview and for the code. And there was this website called BioStars that is like a lot of things in bioinformatics, and people had taken the time to write good posts there and stuff. And then yeah, so it just went like this until in like mid 2021, I had gotten a little bit more comfortable. It's been like a year and a half or so. And I had a former colleague of mine and one of my previous TAs in undergrad at the GC. She was also in Canada and she was a postdoc at the time, and she had started working for Roche. And her PhD was a little bit more computational. So sometimes I would reach out to her and ask some questions for things in my thesis. And then um, she somehow got the impression that I am good at what I'm doing, thankfully. And then they happened to be hiring for their team, and they wanted someone with a background in immunology, which was my major PhD topic. So with a lot of imposter syndrome and a lot of doubting myself and a lot of doubting that I could get a job like this, I applied. Um, they sent me something called a take-home assignment, which is pretty common in a lot of the technical roles or roles that involve like coding and stuff like this. And the assignment was to build a statistics package in R, write all the documentation for it. They give me a data set where they requested that I do very specific functions to do some statistical testing, create some plots, and then write a complete vignette on what my package is doing, describe a workflow of how the data is analyzed, and give some conclusions. I had like I think 72 hours to complete this. I had no idea how to do an R package. I have never written an R package before. And they gave me a book, a public book called Advanced R by Haley Wickham. It's pretty popular. And they're like, if you're stuck, maybe just check the book and see, if you can learn a thing or two. So I spent 72 hours in front of my screen, literally just, working and taking a break to pray and eat and go back to work. I think by the end of the third day, when you're just, like, as I close my eyes, I see like lines of code flowing in front of my eyes. It was very intense. But I think it worked out. Then they kind of did like a follow-up interview to talk about the code, and they told me like how much of that stuff have you done before versus have you not done. And I think there was like a list of 10 things, and out of the 10 things I'm like maybe I did 3 out of them before, but the 7 were new to me, so like I didn't really hold back. um so eventually, I think I got lucky. Alhamdulillah, يعني توفيق إنه the manager was looking more for the hiring manager was appreciating the potential. Alhamdulillah, I had a strong foundation on the biology side. And he thought like I could pick up the computational part as I start working on projects. They've seen that there were some things that I haven't done before, and I was able to do them in a good time frame. Um, yeah, and then yeah, it started like I got hired, started working as a computational biologist. The first project I worked on was a single cell RNA-seq project, which I had not touched before. Like all I've done in my life before was just bulk RNA-seq and microarray. And I started and I'm like, there you go. This is a single cell RNA-seq project. Go analyze the data and go answer these questions. So again, I had, following the same path that I did. No panicking. What do people do to analyze this data? I looked online, I looked for vignettes, I looked for packages, and then I just one, step at a time, I worked my way through. And then slowly I became good at being a computational biologist for about 3 years at Roche until October of last year when I got offered to move to Genentech. And with that movement, I was supposed to be at the same department that I was working on before. So when I was at Roche, I had a manager in Genentech because, Genentech is owned by Roche. And long story short, I was working with one person at Genentech all my time, and that person hired me to move to San Francisco to be at the same department. But between the time I signed my acceptance and the time I actually went there, he got moved to what is now called the BRAID department, which is Biology Research and AI Development, which department completely focused on AI methods and deep learning and machine learning and so on. So now, instead of me working in the space of being a computational biologist is just someone who can use the existing tools and packages to analyze biological data and basically very biology centric workflow. The braid is someone who is trying to develop new methods. So I had to, now that was kind of, I call it my second transition because now I needed to not just be a user of these tools, I needed to understand deeply how these tools work, what's the math behind, how do models work, how are models being trained. And then I started learning and teaching myself how things work. And slowly, bit by bit, I, tried to figure things out. And I'm still learning, day by day. I'm still like trying to read papers and understand things. And sometimes things I don't know are very, very basic that people take in like their first and second year of undergrad if they've done like a computer science program or a math and statistics program or something. I'm okay with this because I also don't know things in the on the biology side, which I know from my second year of pharmacy. So that's fine. To each their own. The long story short is learning is going to continue for as long as one is in this field. And things are very dynamic and changing. And as long as you're open to um, feeling idiot at sometimes and learning and just realizing that no one really knows it all. So some people are good in certain parts and weak in certain other parts. And as long as you just embrace this and have an open mindset and not really feel insecure about it, then you should be okay. So that's like a very compressed version of my transition, my twice transition or double transition into from being a person who cannot really write a code, a line of code, or cannot really understand what the microarray people do to the data, um, to someone trying to develop models now. Any questions?
عاش جدا يا دكتور ما شاء الله.
A good question. I think I would have gotten to a postdoc had I not gotten any position anywhere else. Like um my priority was to go into industry. I actually also looked at postdocs at industry. Like Genentech has a good postdoc program. But I think we talked about this also at the event, like academia versus industry. That was a little bit of a also a very tough decision and a process that I went through of trying to convince myself to get away from academia. But I mean, had I not gotten any position except for a postdoc, I probably would have accepted it because, um, yeah, because I had, yeah, because, I mean, the first reason would be I had a family to feed, and then, I guess I usually when I make these decisions, I usually try and go with an open mind that I don't really know what is good for me. يعني محدش عارف الخير فين. I might be thinking one thing that this is really the best thing that can happen for me, and it turns out to be the worst thing that happens for me. For example, I also talked about this in the um, last summer that I had a really tough relationship with my PhD advisor, and he let me down on multiple fronts, and like it was just a terrible experience. I think this was one of the drivers that drove me away from academia. Um, but maybe if I had a good experience, I would have, I would have been more motivated to stay in academia, do a postdoc, and have like the classic pathway. In retrospect, I think I'm much, much, much happier um, being in industry, and I'm glad that this worked out for me the way it did. So now when I look back, maybe my relationship with my advisor is not a bad thing. Maybe it was just meant to be this way to sway me, away from academia towards industry. So, yeah, the short answer is, had I not gotten anything except for a postdoc opportunity, I probably would have gone for it, because at the end of the day, I'm trying to be responsible and I have a family to feed. But at the same time, just accepting that if I had, you know, explored different opportunities, and this is the opportunity that came across my way, then or that worked out eventually, and just trusting that inshallah this is what's good for me, regardless of how I see it now or at the time. As long as I've done my due diligence in exploring everything and there was only one thing that worked out, then hopefully this is what's good for me. Yeah.
Thank you يا دكتور.
It's been a pleasure. يعني إن شاء الله إن شاء الله هنشوف بعض كمان 3 أسابيع بس. يعني hopefully you learned one or two things in that course.
Yeah.
I apologize for any shortcomings on my end. I tried my best given the amount of time I had and the amount of energy that I had at times to do my best in teaching that course. It was harder than expected in terms of the time it needed to prepare and make slides and everything. But hopefully it was worth it for you. يعني إن شاء الله ربنا ينفع بكم جميعا بإذن الله. إن شاء الله كلكم تبقوا أحسن مني. That's the goal.
شكرا جدا دكتور عمر، يعني كان كورس جميل جدا، وشكرا على المجهود الرائع، يعني ميرسي جدا.
شكرا لحضرتك برضو على التنظيم. I was just يعني أنا كنت باجي بس بدخل أتكلم وأمشي، فجزاكم الله خيرا على التدريس على على عايز أقول كلام راح على التنظيم. جزاكم الله خيرا على التنظيم for the students for being here. وإن شاء الله إن شاء الله تكونوا اتعلمتوا حاجات كويسة، وإن شاء الله تبقوا أحسن مني كتير في الديب ليرنينج، وتعلموا اللي بعديكوا واللي بعديكوا واللي بعديكوا إن شاء الله.
شكرا جزيلا يا دكتور، جزاك الله خيرا. And you have had a profound influence on us for the last 10 sessions, and I hope we will convene again soon for the project capstone. شكرا
إن شاء الله.
جزيلا على كل حاجة. شكرا، جزاك الله خير.
جزاكم الله جميعا خير إن شاء الله. يلا، السلام عليكم.
وعليكم السلام ورحمة الله وبركاته.
وعليكم السلام.